All. In this video, I'll be telling about the series regulator. This is the block diagram of a series voltage regulator. In a series voltage regulator, the control element will be in series with the load. In other words, we'll have an unregulated input and a regulated output. In between, we'll have a control element which is going to regulate the voltage. The output is taken as a feedback, fed it through a sampling circuit to the comparator. The comparator compares the reference voltage along with the output signal and sends an error signal, or the comparator signal is sent to the control element, which acts as a control signal to control the change in the output. If in case there is a change, which means an increase or decrease in the load side, will be compensated by the error signal that is produced, or the control signals that is produced by the comparator circuit. The basic circuit of a series voltage regulator is the transistor series voltage regulator shown here. It is also known as emitter follower voltage regulator. Here the transistor Q acts as the control element, or which is called as the pass transistor here. A large proportion of the change in the input voltage appears across the transistor, and therefore the output voltage remains constant. Now the Vout is nothing but the difference of Vz minus Vbe. And assuming that Vbc is constant, so Vz is also constant because it's a voltage across the Zener diode. Let us consider few cases, or at least one or two cases, by which we'll check whether the output voltage is regulated or not. First case, if there is an increase in the input voltage and that causes a change, means output voltage is also increasing. So case 1, there is an increase in the input voltage which affects or which reflects in the output voltage, and there is an increase in the output voltage. And we have to compensate this, or to regulate, to get a regulated output, we have to check how the circuit is working. An increase in the Vout will also increase the VBE, will decrease the VBE, and because Vz is fixed, and since VBE is reduced, obviously the level of conduction is also reduced. This means the RCE, the resistance across the collector and the emitter of the transistor, will increase, which in turn causes an increase in the voltage across the collector and emitter, which means when there is a decrease in the VBE, conduction increases and obviously VCE increases. Now because of this VCE, obviously the output voltage is reduced. So a change that happened is compensated. A slight increase in the output voltage which happened earlier is now decreased by the feedback that is passed. Now this can be assumed for the next case, where if the input voltage is reduced also. So the reflection will be that output voltage will be reduced, accordingly there will be a change in VBE, conduction will be changed in the transistor, and so there will be a change in VCE which will reflect in the change in the output voltage. So we'll consider one more case where if there is a change in the load. Earlier we considered there was a change in the input voltage, and because of this, which there was a change in the output voltage also. Now there is a change in the load. So let us check what is the effect of the change in the load on the output voltage. So what happens in that case is, it can be an increase or decrease, whatever may be the case. Let us assume that IL is increasing, by which obviously RL is reduced, and therefore Vout will also, which means the output voltage is also reduced, and therefore VBE will obviously increase. Because of this, there will be a reflection in the conduction level, and which means the conduction level will be increasing in the transistor, leading to the decrease of the RCE, and because of the decrease in the RCE, there will be a slight increase in the input current in order to compensate the decrease in the RL. Therefore, since Vout is actually IL into RL, therefore it remains constant. And Vout is also Vz minus Vbe. When IL is equal to 0, current drawn from the supply is approximately IZ, and in a simple simple voltage regulator or a Zener regulator consists of a resistor and a Zener diode, which has to supply only the IB. Therefore, emitter follower regulator is more efficient than a simple Zener regulator, but it has its own limitations. This circuit has its own limitations. The output voltage cannot be maintained constant because there will be a fluctuation in both VB and VZ. In order to compensate there will be change in the room temperature. So obviously you can't expect the constant VB or VZ. And when there is a change in VB, obviously there will be a change in the load also. With the increase in the load, there will be a change in VBE, and output voltage cannot be changed because there is no provision provided in the circuit. It's a constant fixed one, and good regulation is not obtained at high currents because of small amplification provided by only one transistor, and which means poor regulation. And ripple suppression is also there with respect to input variations. Power dissipation is large, and so because of which we'll move on to another circuit where we'll have slight modifications in this circuit.